Welcome to the deep dive. So you use computers every single day, right? I mean, from the smallest smart device maybe in your pocket to the powerful workstation on your desk. But have you ever really stopped to think about the intricate dance happening inside that magical box?
It's easy to just use them.
Exactly. So today we're peeling back the layers. We want to explore the foundational elements, the invisible orchestrators that make your entire digital life possible.
Right. And it's surprisingly easy, actually, to take for granted the incredible complexity that just hums beneath those sleek interfaces we interact with all the time.
Totally.
So our mission today really is to journey from the very, very smallest unit of digital information all the way up to the complex systems that manage everything.
The whole stack.
The whole stack, yeah.
Yep.
Helping you truly grasp how hardware, software, communication, how it all works together in concert. And we're drawing from a fascinating collection of sources today, covering everything from, basic computer overviews, data representation, the real nitty-gritty of CPU operations, logic gates, and that unsung hero, the operating system.
Okay, let's unpack this then. Get ready for some serious aha moments about your digital world. So if we're going to understand what makes these machines tick, where do we even begin? It feels like maybe starting with the very smallest building block makes the most sense.
Absolutely. I think that's the only way, really. The foundation's truth of all digital information, doesn't matter how complex, it boils down to a single concept, the bit.
The bit.
Think of it as a tiny, tiny binary switch. It's either off, which we call 0, or it's on, which is 1.
Right. Just two options.
Those two states are the entire vocabulary a computer understands. That's it.
And then these bits, they group up, right?
Yeah.
To form something, well, more meaningful.
Exactly. A group of 8 of these bits forms a byte.
Okay, the byte. Hear that one a lot.
Yeah. And a byte is particularly important because it's the smallest amount of memory that standard computer processors typically handle in a single operation. It's like their fundamental unit of work,
Got it. And the power of these tiny switches is exponential, isn't it? I remember hearing something about powers of 2.
That's exactly right. That's where the real magic begins. If you have n bits, you can represent 2 to the power of n possible values.
Okay.
So while 1 bit gives you just 2 values, 0 or 1.
On or off.
Right. But just 8 bits, 1 byte can represent 2 to the power of 8. That's 256 different values.
Wow, okay. So you go from just on-off to 256 possibilities pretty quickly.
Instantly. Imagine going from a simple light switch to controlling 256 different shades of light just by adding, 7 more switches. This binary system, it's the ingenious way computers represent all the diverse data you interact with every day.
So how does that translate into something we understand, like text or numbers? How does my name, for instance, become a series of zeros and ones?
It's all about established codes, agreed upon standards. A single character of text, for most Western languages anyway, often takes 1 byte, those 8 bits, using character sets like ASCII.
Okay, ASCII. Heard of that.
Yeah, but for larger character sets, like, say, used in Asian languages with thousands of characters, it can expand to 2 bytes or 16 bits. That gives you many more possibilities.
Makes sense. And numbers, like whole numbers.
Well, whole numbers can vary wildly in size. A single byte can hold a small range, maybe -128 to +127. But for truly massive whole numbers, like in the range of plus or minus 9 quintillion,
Whoa.
that requires 8 bytes.
That's an almost incomprehensible range. And what about more complex numbers, like decimals? Or for scientific calculations?
Yeah, those are typically called floating point numbers. They're stored using a form of scientific notation, essentially.
Okay.
A single precision floating point number uses 4 bytes and gives you about 6 decimal digits of accuracy. Double precision uses 8 bytes for roughly 15 digits of accuracy.
Much more precise.
Much more. And even things like date timestamps or currency values, they typically occupy 8 bytes as well, just to ensure that high precision.
It's fascinating how everything from a simple character to a complex calculation just boils down to these bits and bytes. But what about something, well, inherently visual, like a picture, or something abstract like sound, like a song? How do those get stored?
Right, good question. Picture data is usually stored as a raster or bitmap, which is essentially a rectangular grid of tiny dots, pixels.
All pixels, yeah.
The memory it takes depends on the color or shade resolution you want. For a simple black and white image, it's just 1 bit per pixel, on or off.
Black or white.
Exactly. But for, say, 256 colors, it's 8 bits per pixel, and high-resolution scanners can even use up to 48 bits per pixel to capture incredibly fine detail.
Wow.
And the colors themselves, they're just represented by numbers indicating the intensity of red, blue, and green light, RGB.
And sound?
Yeah.
You can't really see air pressure, so how is that turned into numbers?
Yeah, that's a bit different. Sound data is recorded as a sequence of numbers that represent the variations in air pressure over time. Like snapshots.
Snapshots of the sound wave.
Kind of, yeah.
Mm.
For CD quality audio, this means capturing 44,100 of these snapshots or samples every single second.
44,000 times a second.
Per second, yeah. And each sample is usually a 16-bit number, representing the pressure level at that instant.
Okay.
Video data, then, is basically just a rapid series of those pictures or frames, typically displayed at 24 to 30 frames per second for high quality. Think of it like a digital flipbook.
That sounds like an enormous amount of data accumulating very, very quickly. This must be why compression is so critical, right? To stop our hard drives from just bursting and our internet from crawling.
You've absolutely hit on a critical point there. Picture files, sound samples, and especially video frames. They can be huge. Absolutely massive. Compression is vital to manage this volume.
So how does that work?
Well, we generally talk about two main types, lossless and lossy.
Okay. Lossless sounds safer.
It is, in a way. Lossless compression reduces file size without losing any of the original data. Zero loss. Think of it like neatly folding a blanket to fit it into a smaller box.
Right.
It takes up less space, but it's still the whole blanket. You can unfold it perfectly. Text compression works like this, or some algorithms for pictures that describe uniform areas geometrically. These typically achieve compression ratios from maybe 1.5 to 8 times smaller.
Okay, that's useful. But what about lossy compression? That sounds a bit riskier, like you're actually throwing something away.
You are, yeah. But hopefully intelligently so. Lossy compression, like you see in JPEGs for pictures or MP3s for sound.
Yeah, common formats.
Right. It retains the major attributes of the data, but discards some of the less critical details that your eye or ear might not even consciously perceive anyway. It's like taking a super detailed drawing and simplifying some background elements. You still recognize the main subject perfectly, but maybe some subtle shading is gone.
Mm-hmm. So you lose some info, but hopefully not stuff you'd notice.
Exactly. And the user can often choose the balance quality versus file size. This allows for much, much higher compression ratios. Like JPEG can often achieve 25x compression. MPEG for video can hit 50 to 100 times smaller.
Wow, that's huge savings.
It is. And the minimal loss is often acceptable because, a single video frame isn't on screen for long, and consecutive frames are often very similar anyway. It's a really clever trade-off.
So, okay, we have bits and bytes representing everything, compression helping manage the sheer volume. But how do these hours and ones actually do anything? This is where logic gates come in, right? The first steps of computer thinking.
Indeed, yeah, now we're getting to the action. At their core, computers are fundamentally just simple collections of digital switches.
Yeah.
The primary components inside integrated circuits, or ICs, are transistors.
Transistors. Billions of them on a chip now, right?
Billions, yeah.
Yeah.
It's mind-boggling. These tiny components, incredibly small now, act like miniature faucets, basically controlling the flow of electricity, on or off, 0, 1.
And these transistors, they're controlled by something called Boolean algebra. That sounds like a math class I might have tried to avoid. But here it's fundamental.
It is absolutely fundamental. Boolean algebra, developed by George Boole way back, is the mathematical basis for all computer logic design. It involves constants and variables that can only take on two values, true, false, on, off, or for us, 0, 1.
Okay.
And the three fundamental operations are A and D, or R and not.
Can you give us a quick tangible example of one of those, like A and D? How does that work?
Sure. Think of an A and D like a really strict security check. It only lets a signal through if both inputs are true, or by one. So if you need both a key, A and D, a password to unlock something, that's an A and D operation. Both must be present.
Okay, makes sense. And OR.
For an OR gate, it's more flexible. You get the signal through if input A is true or input B is true, or both. So you get access if you have the key or the password.
Got it. And not.
Not is just simple inversion. If the input is 1 on, the output is 0 off, and vice versa. It just flips the state.
So
there's also exclusive OR, XOR, which is true if either input is true, but crucially not both. Think of like a hallway light with switches at both ends. If both switches are up, the light's off. Both down, light's off. But if one is up and one is down, the light's on. That's XOR logic.
Huh. So these incredibly simple A and Ds, ORs, and nots. That's what allows computers to do complex calculations, like adding numbers or comparing values.
Precisely. These basic logic gates combine together in circuits to form what's called combinatorial logic. Here, the results, the outputs, depend only on the current inputs. This is used for fundamental operations like arithmetic, controlling data movement, making comparisons.
Okay.
Then there's sequential logic. Here, the results depend not only on the current inputs, but also on the results of previous operations. It has memory.
Ah, memory.
Yeah. This is crucial for things like counters or memory elements like flip-flops, which can literally remember a state, hold on to a 0 or a 1. This elegant simplicity is exactly how a computer builds up incredibly complex functionality from these foundational binary blocks.
Okay, we've explored the absolute bedrock, data storage, compression, basic logic gates doing tiny decisions. Now let's talk about the real powerhouse, the maestro of this digital orchestra, the central processing unit, the CPU. This is truly the computer's brain, isn't it?
That's a perfect analogy, yeah.
Yeah.
The CPU is indeed the heart, the brain of the computer. It tirelessly processes data by executing instructions.
And it has different parts inside doing different jobs.
It does. It's typically made up of three primary components, each playing a crucial role. There's the arithmetic logic unit, or ALU,
Okay, ALU.
the control unit, or CU,
CU.
and the interface unit.
So if the CPU is the brain, is the ALU like the math part, the logical part, the meticulous accountant crunching numbers? Or is it more like the problem solver getting directions?
You're absolutely on the right track there. The ALU is indeed the calculator and the decision maker. It performs all the arithmetic addition, subtraction, you name it, and those Boolean logical calculations we just discussed, like comparing two numbers. It's the engine for direct computation.
Okay. And the control unit, what's its job? Is it like the manager telling everyone what to do?
Exactly. The control unit is the ultimate orchestrator, the manager, the conductor. It directs the processing of instructions and manages the flow of data within the CPU itself. It makes sure every operation happens in the right order at the right time.
Got it. And the interface unit.
That acts as the CPU's communication hub. It's responsible for moving instructions and data between the CPU and all the other hardware components like memory or your hard drive. It handles the traffic in and out.
Moving inside the CPU itself, we also have something called registers. These are like the CPU's super speedy scratch pad, right? Always ready for quick notes and calculations.
That's a great way to put it, yeah. Registers are tiny permanent storage locations right inside the CPU, designed for incredibly fast access, way faster than main memory. They hold data, memory addresses, or instructions that the CPU needs to access very quickly or frequently for the program it's currently executing. Think of them as a chef's immediate prep area. They hold exactly what's needed for the very next step, right there on the cutting board.
Are there different kinds of registers, each with a specialized role?
Yes, very much so. You have general-purpose registers, which are usually user-visible in assembly programming. They can hold intermediate results or data values, like maybe a loop counter in your code.
Okay.
But then there are several crucial special-purpose registers that are absolutely essential for the CPU's basic operation. For example, the program counter, or PC, also called the instruction pointer. It's like the chef's checklist, always holding the memory address of the next instruction the CPU needs to fetch and execute.
So it knows what to do next.
Exactly. Then the instruction register, or IR, is where the current instruction sits while it's being decoded and executed. The memory address register, MAR, holds the address of the specific memory location being accessed for reading or writing data. And the memory data register, MDR, is like a two-way loading dock. It temporarily holds data being transferred to memory or from memory.
Okay, that makes sense. So that takes us naturally to memory itself, often called RAM, random access memory. This is the CPU's main but short-term workspace, where it keeps everything it's actively working on.
That's right. Memory, also known as primary storage or working storage. It consists of those bits, zeros and ones, grouped into bytes. And crucially, it holds both the instructions and the data of a computer program that's currently running.
Both things in the same place.
Yes. This is known as the stored program concept, and it's a truly revolutionary idea that underpins the von Neumann architecture, which still largely defines modern computers today. Before this, programs were literally hardwired or loaded manually step by step. Now, a program can be changed just by loading new instructions into memory. It's fundamental.
And speaking of RAM, there are different types. I know DRAM is common, but what's SRAM all about?
There are different types, yeah. DRAM, or dynamic RAM, is the most common type you find for main memory. It's relatively cheap and uses less power, but it's volatile.
Volatile meaning it forgets when the power goes off.
Exactly. And not just that, it must be constantly refreshed thousands of times per second just to retain its data while the power is on. Like
Yes.
a leaky bucket needs constant refilling.
Okay.
SRAM, or static RAM, is faster but also more expensive, and it's also volatile. But because it doesn't need that constant refreshing, it's often used in smaller amounts, like in cache memory.
Cache, right. That
Ah.
super fast memory close to the CPU.
Precisely. Its speed is paramount there for high-speed access to frequently used data and instructions.
What about memory that doesn't disappear when the power goes off? Like the stuff that makes your computer boot up in the first place?
Ah, right. That's non-volatile memory. ROM, or read-only memory, is a classic example. It stores software that isn't expected to change, like the initial program load or bootstrap instructions, the very first code that runs to load the operating system when you turn your computer on.
Okay, so you can't easily write to ROM.
Traditionally, no. Though now we have things like EEPROM and flash memory. These are also non-volatile, but you can write to them, albeit slower than RAM. They're faster than traditional disks, though, and super useful for things like USB drives, solid-state drives, SSDs, or firmware storage.
Okay, so the CPU has its temporary scratchpad registers and RAM as its main short-term workspace. How does the CPU actually use all of this to run a program? This is where the famous fetch-execute cycle comes in, isn't it? The core heartbeat of computation.
Absolutely, the fetch-execute cycle. It's the fundamental two-cycle process by which a CPU runs programs. It's this elegant, relentless dance of operations that happens literally billions of times every second in a modern processor.
Billions. Wow. Okay, walk us through what happens first in this rapid-fire cycle.
The first step is fetch. The control unit takes the memory address stored in the program counter, PC.
The address of the next instruction.
Right. It uses that address to find the next instruction in memory, RAM. It then loads or fetches this instruction from memory and places it into the instruction register IR within the CPU. So the PC points to the recipe step, and the IR now holds that specific step to be processed.
Okay, instruction fetched, then what?
Then the CPU actually does something with that instruction. That's the execute phase. The control unit decodes the instruction in the IR and signals the appropriate components, usually the ALU, to perform the required operation.
Like adding numbers or moving data.
Exactly. It might involve calculations using the ALU, moving data between registers, transferring data to or from memory via the MAR and MDR, or even changing the flow of the program by updating the program counter to jump to a different instruction instead of just the next one in sequence.
And then the PC gets updated for the next cycle.
That's right. Once the execution is complete, the program counter is typically incremented to point to the next instruction in memory, ready for the next fetch cycle. This simple, repetitive two-step fetch-execute loop applies to every single instruction a computer performs. It illustrates the fundamental simplicity at the heart of computation, no matter how complex the final result seems.
It's incredible how much complexity emerges from that simple cycle, repeated billions of times a second. But how does all that data and all those instructions actually move around? Between the CPU, memory, maybe the graphics card, other components? What are the pathways?
That's where buses come in. Buses are the physical connections, literally bundles of wires or sometimes optical conductors that act as the vital highways for data transfer between different components inside your computer.
Okay, information highways.
Pretty much. They carry the actual data, the addressing signals to pinpoint specific memory locations, control signals to coordinate operations, are you ready, data is coming, and sometimes even electrical power.
So like a super multi-lane highway within your computer, are they all the same design?
Not exactly. We can categorize them in a few ways. One is how they transmit data. Parallel buses send multiple bits simultaneously over multiple wires, like 8, 16, 32, or 64 bits at once. They offer high throughput over short distances, which is why they're used for the internal pathways on your motherboard connecting the CPU to RAM, for instance.
Faster for short hops.
Right. Serial buses, on the other hand, send data one bit at a time, sequentially, over a single wire or pair. It sounds slower, but they can often achieve higher effective throughput over longer distances because they suffer less from electrical interference and timing issues, skew, than parallel buses.
Ah, okay. That's why things like USB are serial.
Exactly. USB, SATA for drives, Ethernet, those are common serial buses, great for external connections or longer internal runs.
And do they all send data in both directions at once? Or is it more like a one-way street sometimes?
Good question. It varies. There's simplex transmission, which is strictly one-way only, like a radio broadcast. Half duplex allows two-way communication, but only one direction at a time. Think of a walkie-talkie where you have to say, over.
Right, push to talk.
Yeah. And full duplex allows simultaneous two-way transmission, like a normal phone call where both people can talk and listen at the same time. Most modern buses aim for full duplex where possible.
And how they connect. Just one thing to another.
Sometimes that's point to point, like a dedicated cable connecting your CPU directly to a specific memory controller. Or they can be multi-point or broadcast, where multiple devices share the same bus, like older parallel buses or networks like Ethernet, where multiple computers connect to the same cable or switch.
Now, what about the actual action verbs of the CPU, the specific commands it understands? What kinds of instructions can it perform that make software actually do things?
Right, the instruction set. This defines the entire repertoire of functions a processor can perform. These are the fundamental commands the CPU understands, telling it what task to do and where to find the data or put the results.
Can you give some examples?
Sure, common types include data movement instructions, like load, bring data from memory into a register, and store, save data from a register back to memory. Then there are all the arithmetic operations, add, subtract, multiply, divide. And the Boolean logic operations we talked about earlier, ND or XOR, not add, for comparisons and decision-making.
Okay.
You also have bit manipulation instructions for very fine-grained control over individual bits within a byte or word. And crucial program control operations like JMMP, go to a different instruction address, and branch H, jump conditionally, like jump if this value is 0. These allow programs to make decisions and loop.
And for something like multimedia or graphics, are there specialized instructions for that?
Absolutely.
Yeah.
Modern CPUs often include multiple data instructions, especially SIMD, single instruction, multiple data. These are incredibly powerful. They allow the CPU to perform a single operation, like an addition or multiplication, on multiple pieces of data simultaneously in parallel.
So it can process like multiple pixels at once.
Exactly. Or multiple audio samples. It significantly speeds up tasks common in graphics, video encoding, scientific computing, and AI. There are also stack instructions, POH, POP for last in, first out data structures, and others.
And every instruction has those two parts, the command and the data reference.
Pretty much, yeah. Each instruction has an OPIA code, operation code, which specifies what task to perform, like add or load, and usually one or more operands, which indicate the data locations, like register numbers or memory addresses, or sometimes the actual values involved in the operation.
We've now covered the very foundation, bits, bytes, logic, the CPU, memory, how they communicate. But all of this intricate hardware, this symphony of zeros and ones, needs a master orchestrator, right? Something that ties it all together and makes it usable for us. This, of course, is the operating system, the OS.
Indeed. And it really begs the question, what exactly is an operating system, fundamentally? It's essentially a collection of programs, a big software suite that integrates all of a computer's hardware resources.
CPU, memory, disk.
All of it.
Yeah.
And makes those resources available to you and your application programs in a productive, timely, and efficient manner. It's the great mediator.
And if we didn't have an OS, what would that look like in practice? It'd be like living in the digital Stone Age.
Oh, it would be pure chaos. Utterly impractical. Imagine a computer without an operating system. You literally have to load program instructions by hand, maybe flipping switches bit by bit.
Seriously.
Yeah, there'd be no user interface beyond maybe some basic input-output routines, lights flashing, maybe a simple text display if you were lucky. The system would just sit there, completely idle, waiting for your manual input for everything.
Wow.
There'd be no concept of easily storing or retrieving files, no automated control over peripheral devices like printers or network cards, and crucially, you could only run one single program at a time, and it would probably halt after each small task, waiting for you again.
That sounds incredibly tedious. Unusable, really.
Completely unusable for modern computing. So the OS steps in and makes life a whole lot easier for us, acting as this essential middleman between the hardware and the user or applications.
So what are its core services then? The things we benefit from constantly, maybe without even realizing it?
Well, first and foremost, it provides a user interface. That could be a command line interface, CLI, where you type commands.
Like in the old days. Or on servers sometime.
Right. Or more commonly now, the graphical user interface, GUI you're probably used to with windows, icons, menus, pointers, makes it much more intuitive. It also manages, loads, and executes all your programs. It finds the program file, loads it into memory, gets it running on the CPU.
Okay.
It's the ultimate hardware resource manager. It doles out CPU time, allocates memory, handles access to the disk drives, manages network interfaces, basically controls access to all the physical parts.
And I can run multiple programs at once, even on a single processor, thanks to the OS. That's multitasking.
Yeah, precisely. That's multitasking, or sometimes called multi-programming. The OS simulates simultaneous execution of multiple programs on a single CPU by rapidly switching between them. It happens so fast, it gives the illusion that everything is running at the same time.
Ah, the illusion.
Yeah. Now, if you actually have multiple CPUs or multiple cores within a CPU, then you get actual simultaneous processing, which is technically multiprocessing.
Got it.
The OS also handles all your file management. It provides those familiar directory or folder structures, gives you tools to copy, move, delete, and find files. And it includes essential security mechanisms to control who can access what file.
Keeps things organized and safe.
Exactly. It provides I/O support, handling all the communication with devices like your keyboard, mouse, printer, monitor. It often uses low-level software like the BIOS, basic input-output system, and specific device drivers to talk to each piece of hardware. And, of course, it's responsible for bootstrapping that whole intricate process of starting your computer when you hit the power button, getting itself loaded and taking control. And finally, it provides fundamental security and protection. Protecting the OS itself from users or bad programs, protecting users from each other on multi-user systems, and preventing unauthorized access to data and resources.
It sounds like the OS is really the central nervous system, doing a million things at once. Is there a core part that's always running, like the brainstem, even when you think nothing much is happening?
There is, yeah. That's the kernel. The kernel is the memory resident part of the OS. That means it's always loaded into memory from the moment your computer boots up until you shut it down.
Always there.
Always there. It contains the absolute essential services for managing memory, processes, running programs, and access to secondary storage like your disk drives. The core functions live in the kernel.
And the other parts, like utilities or specific commands.
Those are often non-resident parts. These are less frequently used programs, software tools, system utilities, maybe command interpreters that are stored on disk and loaded into memory only when you actually need them. This saves valuable RAM for your applications.
Are all operating systems organized the same way internally?
Yeah.
Or are there different philosophies, different architectures at play?
No, definitely not all the same. There are distinct architectures for how the OS services are organized internally, and each has its own trade-offs in terms of performance, stability, security, and complexity.
Like what?
Well, the classic approach is the monolithic kernel. You find this in systems like traditional UNIX and Linux. Basically, all the main OS services, process management, memory management, file system, device drivers run together in one single large program, the kernel, in a privileged mode.
All in one big chunk.
Yeah. It's generally simpler to design initially and can be very fast because communication between different parts is just internal function calls. But the downside is that a crash or bug in one part, say a faulty device driver, can potentially bring down the entire system, and it can be harder to modify or extend safely.
Okay, so fast, but maybe less stable. What else?
Then there's the hierarchical or layered approach. Here, the OS services are separated into distinct, independent layers. Each layer only uses services from the layer directly below it. Requests get passed down through the layers. Systems like Multics pioneered this, and some later versions of Windows adopted aspects of it. It can make debugging and modification easier because layers are isolated.
Sounds more organized.
It can be. And then there's a more modern approach, the microkernel. I've heard that term thrown around.
The microkernel design philosophy is quite different. It aims to put only the absolute minimum essential functionality into the kernel itself, typically just basic process communication, maybe some memory management fundamentals, and low-level scheduling. So a really tiny kernel.
Exactly. Other traditional OS services, like file systems, full device drivers, networking stacks, they run as separate server processes outside the kernel, in user space, just like regular applications. Mac OS X, or Mac OS now, uses a hybrid approach with a microkernel component, MOC.
What's the advantage of that?
The main arguments are better stability and security. If a server process like a file system crashes, it doesn't necessarily take down the entire kernel or the whole system. You might just need to restart that one service. And isolating components like drivers outside the kernel enhances security. There's less code running with full system privileges. The potential trade-off is performance, as communication between these servers and the kernel can involve more overhead than simple function calls within a monolithic kernel.
Interesting trade-offs. So beyond our everyday desktops and laptops, what other types of operating systems are out there, each specialized for a different kind of task or device?
Oh, there's quite a wide range, each tailored for specific needs and constraints. Beyond the single user, multitasking systems like Windows, Mac OS, and desktop Linux that most of us use daily.
Yeah, the common ones.
You have mainframe operating systems. These are designed for large-scale, high-volume computing. Think massive transaction processing, huge databases, supporting hundreds or thousands of users simultaneously, often with a strong emphasis on batch processing and high I/O throughput.
Big iron systems.
Big iron, exactly. Then you have network operating systems or server OSs like Windows Server or specialized Linux distributions. These are optimized for running on servers, providing services to client computers over a network. They usually have enhanced security features, better reliability, and tools for managing network resources and users.
Okay. What about for our phones or even smaller devices? They definitely have operating systems.
Absolutely. For handheld devices like smartphones and tablets, you have mobile operating systems, iOS, Android being the giants. These are specifically tailored for unique constraints like limited battery power, smaller memory footprints, touch-based input, and managing wireless connectivity seamlessly.
Right, different needs.
Then there are real-time operating systems, or RTOS. These are critical for applications where processes must complete their tasks within very strict, guaranteed time deadlines. A delay could be dangerous or catastrophic.
Like what kind of applications?
Think air traffic control systems, industrial process control like in a factory,
Yeah.
robotics, anti-lock braking systems in cars, medical equipment like pacemakers. Timing is absolutely paramount.
Okay, yeah, you don't want those to lag.
Definitely not. And somewhat related are embedded systems. These are specialized OSs, often very stripped down, designed to control a single piece of equipment or device. They might be in your microwave oven, your car's engine control unit, a digital camera, a smart thermostat.
They're everywhere.
Pretty much everywhere these days. The software, including the OS, is often stored directly in ROM or flash memory on the device itself, like in GM's old Delphi system for cars. And finally, you have systems designed for distributed computing, where the OS manages resources and processing power spread across multiple interconnected computers, like in a network cluster. This allows for massive computational power, fault tolerance, and resource sharing.
It's amazing how many different forms the OS takes depending on its specific role. Now, let's get into how the OS juggles all these different programs and tasks running at the same time, especially on the CPU. It comes down to something called processes, right? A program in action.
That's exactly right. A process is essentially a program that is currently in execution. It's an active entity, progressing sequentially through its instructions. The OS assigns each process a unique ID, like a tracking number. And every process is like a temporary digital worker. It requires resources to do its job, things like CPU time, to execute instructions, memory space to hold its code and data, and maybe access to files or I/O devices. Think of the program file on your disk as the static blueprint, but the process is when that blueprint is actually being built and doing something active.
Right. The program is passive, the process is active, and the OS has to keep track of all of these active processes, right? Like a meticulous supervisor managing all the workers.
Yes, that's crucial. The operating system uses a data structure called a process control block, PCB, for each and every process it's managing.
PCB. Yeah.
The PCB is like a comprehensive digital dossier, or maybe a passport and a job application all rolled into one. It's a repository holding all the vital information associated with that specific process.
What kind of information?
Things like the process's current state, is it running, waiting, ready? Its unique process ID, the value of the program counter so it knows where the process left off, the contents of its CPU registers, its CPU scheduling information, like its priority, memory management info, limits, page tables, accounting information, CPU time used, and its I/O status, files it has open, devices it's waiting for, everything the OS needs to manage that process effectively.
So a process isn't just running or not running. It actually moves through different states, like stages in a life cycle.
Exactly. Processes transition between several distinct states as they execute. When a process is first created, it's in the new state. Once it's admitted by the OS and ready to run but waiting for the CPU, it's in the ready state, sitting in the ready queue.
Waiting its turn.
Right. When the OS scheduler finally assigns it the CPU, it transitions to the running state, and its instructions are actively being executed. Now, a running process might need to wait for something, maybe for user input or for data to be read from disk. If that happens, it enters the blocked or waiting state. It can't proceed until that external event completes.
So it gets taken off the CPU.
Yes, it leaves the running state so another ready process can use the CPU. Once the event it was waiting for occurs, like the disk read finishes, the OS moves the process back to the ready state so it can compete for the CPU again. And finally, when a process finishes its execution normally, or if it's terminated by the OS for some reason, it enters the terminated state.
It sounds like the OS is constantly playing this intricate game of moving processes between these states, like a really busy air traffic controller.
That's a great analogy. It is like an air traffic controller, guiding processes onto the CPU running state, holding them in waiting patterns, ready queue, diverting them when they need to refuel or wait for clearance, block state, and finally guiding them to their destination terminated. It's
Yeah.
happening constantly and incredibly quickly.
So the OS is constantly managing these queues of processes.
Precisely. When processes first enter the system, they might initially go onto a general job queue, but the ones that are loaded into memory and ready to run are placed on the ready queue. The OS's CPU scheduler then selects a process from this ready queue for execution.
Okay.
Once a process is running, several things might happen. It could finish execution and terminate. It could issue an I/O request, which moves it from the running state to a device queue associated with that specific I/O device blocked state. It might create a new subprocess or child process, or in a preemptive system, its allotted time slice might expire, causing the OS to interrupt it and move it back to the ready queue, giving another process a turn.
And these processes, they can work together sometime.
They can. We distinguish between independent processes, which don't affect or get affected by other processes, and cooperating processes, which can interact. Cooperation might be needed for information sharing between processes, or maybe to speed up a computation by breaking it into parts that run concurrently, or just for modularity in design.
And what about threads? I hear that term a lot too, often in relation to modern software design, making apps feel more responsive. How do they fit in?
Threads. Threads are often called lightweight processes. Think of a thread as an individually executable part within a larger process. A single process can contain multiple threads, all running seemingly in parallel.
So multiple paths of execution inside one program.
Exactly. What makes threads lightweight and so efficient is that all threads within the same process share the same memory space, code and data segments, and other resources like open files. They only need their own separate program counter, register set, and stack.
So they don't need a whole separate PCB each time.
Right, the overhead of creating and switching between threads is much lower than for full processes. This makes them ideal for tasks that can be broken down into smaller parallel parts within the same application, like having one thread handle the user interface while another does background calculations, or having multiple threads process different parts of a large image simultaneously, or handling multiple client requests in a web server. It greatly improves responsiveness and throughput.
All of this complex management of processes and threads leads us directly to CPU scheduling. This is where the OS really flexes its muscles to make sure your computer feels fast and responsive.
Yeah. Choosing exactly which process or thread from that ready queue gets the CPU next.
That's a fundamental function, absolutely critical to your everyday experience with your computer. The CPU scheduler is the component responsible for selecting the next process from the ready queue to be allocated the CPU, and it uses a specific scheduling algorithm to make that decision.
And what are the goals? What makes a good scheduling algorithm? Is it just about speed? It's actually a balance of several, often competing goals. Key aims include fairness, ensuring that all processes get a fair share of the CPU time, and preventing any process from being indefinitely postponed, a situation called starvation. Efficiency or CPU utilization, maximizing the percentage of time the CPU is busy doing useful work, not sitting idle. Response time, minimizing the time it takes from when you submit a request, like clicking a button, until the system starts producing the first response. This is crucial for interactive systems.
Okay, responsiveness.
Right. Also, turnaround time, minimizing the total time it takes for a process to complete from its submission until it finishes entirely. And throughput, maximizing the number of jobs or processes completed per unit of time. Often improving one of these metrics might negatively impact another, so it's a constant balancing act for the OS designer.
So how does the OS decide? Does a process just grab the CPU and hold on to it until it's completely done? Or can the OS interrupt it?
That depends on the type of scheduling being used. There are two main approaches: non-preemptive and preemptive.
Okay, what's non-preemptive?
In non-preemptive scheduling, once a process is given the CPU, it keeps the CPU until it either finishes its task completely or it voluntarily relinquishes the CPU, for example, by requesting an I/O operation or waiting for an event. The OS doesn't forcibly take the CPU away. Examples include the simple first come, first serve FCFS algorithm.
Just line up first in, gets served.
Exactly. Or shortest job first, SJF, which tries to run the quickest task next. Or priority scheduling, where processes with higher priority run first.
But with preemptive, the OS can just yank the CPU away. That sounds a bit ruthless, but probably necessary for making things feel smooth.
It is ruthless in a way, but yes, it's essential for the fluid multitasking and responsiveness we expect today. In preemptive scheduling, the operating system can interrupt a currently running process, even if it hasn't finished or requested I/O, and forcibly take the CPU away to give it to another process. This usually happens based on a timer. The process gets a certain amount of time, and then the OS steps in.
Right, the time slice.
Exactly. Here's where it gets really interesting, especially for interactive systems. Let's look at round-robin scheduling. It's a classic, simple, and very widely used preemptive algorithm, especially for time-sharing systems like your desktop OS. It's basically what makes your computer feel like it's running many things at once.
Okay, how does round robin actually work to achieve that illusion of parallelism?
It's conceptually simple. The ready queue is treated like a circular queue. Each process gets assigned a small, fixed unit of CPU time called a time quantum, or time slice, typically something short, maybe between 10 and 100 milliseconds.
Tiny amount of time.
Very tiny. When a process gets the CPU, a timer is set for that quantum. If the process finishes its current CPU burst before the timer expires, it voluntarily relinquishes the CPU. If it's still running when the timer goes off, the OS generates an interrupt, forcibly stops the process, saves its current state.
Which puts it on pause.
Right. And then moves that process to the end of the circular ready queue. The scheduler then selects the next process from the front of the ready queue and gives it the CPU for its time quantum.
That sounds incredibly fair. Everyone gets a turn. But I can imagine a potential downside. If the time slice is too short, isn't there a lot of overhead just switching between processes all the time?
You've absolutely nailed the trade-off. That's the key challenge with round robin. If the time quantum is very short, you get excellent responsiveness for short interactive tasks, but you spend a significant percentage of the CPU time doing context switches, saving the state of the old process and loading the state of the new one. This overhead reduces overall CPU efficiency.
Okay.
But if the time quantum is too long, the system starts behaving more like FCFS, and short interactive requests might get stuck waiting behind long-running processes, leading to poor response times. So finding the right quantum length is crucial. Typically, it's chosen so that most interactive requests finish within a single quantum.
What about other algorithms that prioritize tasks differently? You mentioned shortest job first earlier. How does that work?
Yeah. Right. Shortest job first, SJF. This algorithm, in its non-preemptive form, looks at all the processes currently in the ready queue and selects the one whose next predicted CPU burst, the amount of time it needs the CPU before its next I/O request or termination, is the smallest.
So it tries to clear out the quick jobs first.
Exactly. And it's actually proven to be optimal in terms of providing the minimum average waiting time for a given set of processes. If you want the fastest average completion, SJF is theoretically the way to go.
But how does the OS know how long the next CPU burst will be? That sounds like predicting the future.
That's the huge challenge. In reality, the OS doesn't know the exact length of the next CPU burst in advance. So pure SJF is impossible to implement directly. Instead, practical systems use various techniques to predict or estimate the length of the next burst, often based on the lengths of the process's previous bursts, using techniques like exponential averaging. So it becomes shortest predicted job first, which is an approximation. There's also a preemptive version called shortest remaining time first, SRTF.
Fascinating how much strategy goes into just deciding what runs next on the CPU. So, okay, we have the CPU being cleverly scheduled, but where does all the data and the program code itself actually live when it's not actively being processed or in those tiny registers? This brings us to memory management and file management, essentially, the digital librarian and the filing cabinet of your computer.
Correct. And managing memory is another absolutely critical job for the OS. It acts like the computer's memory real estate agent. It has to meticulously track which parts of memory are currently being used and by which process, which parts are free, and crucially, allocate and deallocate memory space to processes as they start and finish.
Yeah.
It also needs to provide protection, preventing one process from accidentally or maliciously accessing the memory space of another process or the OS itself. That would lead to crashes or serious security breaches.
Right, keep everyone in their own lane. And historically, it partitioned memory in different ways. I remember hearing about issues like fragmentation.
Yes, early, simpler memory management schemes involved partitioning the physical memory, Fixed partitioning divided the memory into several fixed-size sections or partitions. When a process arrived, it was allocated a partition large enough to hold it. Variable partitioning, on the other hand, kept track of free blocks of memory, holes, and allocated a hole that was just big enough for the incoming process's needs.
Variable sounds more flexible.
It is more flexible in using memory, but it leads to a problem called fragmentation, specifically external fragmentation. As processes are loaded and unloaded, the free memory space gets broken up into lots of small, non-contiguous holes scattered throughout memory.
Like little unusable gaps.
Exactly. You might have enough total free memory available to satisfy a request, but it's not in one continuous block, so you can't allocate it. It's like having enough total parking spaces in a lot, but they're all tiny spots too small for any actual car to fit in. This wasted space reduces memory utilization.
That sounds inefficient. This naturally leads us to wonder, how can you run a program that's actually larger than your computer's physical RAM? This still sounds like magic to me.
It's not quite magic, but it is a truly ingenious solution called virtual memory. It's one of the most fundamental concepts in modern operating systems. Virtual memory cleverly separates the program's view of memory, its logical memory or address space, from the actual physical memory, RAM, installed in the machine.
So the program thinks it has more memory than it really does.
Essentially, yes. It allows programs to have a very large, contiguous logical address space, potentially much larger than the physical RAM available. This makes life much easier for programmers as they don't have to worry about the physical memory limits or write complex code called overlays to manually swap program parts in and out. And it allows more processes to be kept in memory simultaneously, increasing CPU utilization and throughput.
How is this illusion created? What are the main techniques?
It's primarily implemented using two main techniques, often combined. Demand paging is the most common. Here, your physical memory, RAM, is divided into fixed-size blocks called frames, and the program's logical memory is divided into blocks of the same size called pages.
Okay, frames and physical, pages and logical.
Right. The brilliant part is that only the pages of a process that are actually needed at any given moment are loaded from secondary storage, like your disk, into available memory frames in RAM. Pages that aren't currently needed remain on the disk. This demand loading reduces the time spent loading unused parts of a program and significantly reduces the amount of physical memory required to run it.
And the other technique, segmentation.
Demand segmentation is similar in concept, but instead of fixed-size pages, memory is allocated in variable-size segments. These segments often correspond more naturally to a user's logical view of a program, like a separate segment for the main code, one for subroutine code, one for the data stack, one for symbol tables, etc. Each segment can be loaded on demand and placed non-contiguously in physical memory. Some systems combine segmentation and paging.
So with demand paging, what happens if the CPU tries to access an instruction or data that's on a page, but that page isn't currently in physical memory? That sounds like it would cause a big problem.
That situation is called a page fault. It sounds bad, but it's actually a normal, expected part of how demand paging works. When the CPU tries to access an address on a page that isn't currently in a RAM frame, the hardware detects this using a valid invalid bit in the page table, it triggers an OS interrupt, a page fault trap.
So the OS steps in immediately.
Instantly. The operating system takes over. It first checks if the access was even valid. Was it within the process's allowed logical address space? If not, it terminates the process. If it was valid but the page just isn't in RAM, the OS locates the needed page on the disk, finds a free frame in RAM.
But what if there are no free frames? What then?
Good point. If there are no free frames available, the OS must perform page replacement. It has to choose an existing page currently in memory, a victim page, to be removed.
Kicked out.
Kicked out, yeah. If the victim page has been modified since it was loaded, checked using a dirty bit, its contents must first be written back to the disk to save the changes. Then, the desired page can be read from disk into the now freed frame. The OS updates the page table to reflect that the new page is now in memory and the old one is out. And finally, it restarts the instruction that originally caused the page fault. The process continues as if nothing happened, usually seamlessly from its perspective.
That's a complex dance. How does the OS decide which page to kick out? Is it random?
Definitely not random. The choice of which page to replace is critical for performance. The goal of page replacement algorithms is to select the victim page in a way that minimizes the number of future page faults you want to avoid kicking out a page that you'll need again very soon.
Makes sense. So what are some of those algorithms?
Well, the simplest is first in, first out, FIFO. It just replaces the page that has been in memory the longest, the oldest one. Easy to implement.
Seems fair, maybe.
Seems fair, but it doesn't always perform well. It might kick out a page that's still being used frequently just because it arrived early. And worse, FIFO suffers from something called Belady's anomaly.
Belady's anomaly, what's that?
It's a really counterintuitive phenomenon where, for certain patterns of memory access, page reference strings,
Hmm.
increasing the amount of physical memory available, adding more RAM frames, can actually increase the number of page faults when using FIFO.
Wait, more memory makes it worse sometimes. That's weird.
It is weird. It goes against intuition, but it highlights that simple isn't always best in page replacement.
Okay, so what's a better approach than FIFO?
Well, the theoretically optimal algorithm, often called OPT or MIN, would be to replace the page that will not be used for the longest period of time in the future. This would guarantee the fewest possible page faults.
But that requires knowing the future, right?
Yeah.
Which you can't do.
Exactly. Optimal is impossible to implement in a real system because you can't predict future memory accesses. But it serves as a benchmark we can compare other algorithms against it in simulations.
So what's a practical algorithm that works well?
A very common and effective practical algorithm is least recently used, LRU. The idea behind LRU is based on the observation that pages used recently are likely to be used again soon, locality of reference. So LRU replaces the page that has not been used for the longest period of time. It looks backward in time, unlike OPT, which looks forward.
Okay, kick out the one that hasn't been touched in a while. How does the OS track that?
Implementing true LRU perfectly can be complex. It might require hardware support like counters or stacks associated with pages, or significant software overhead to track usage times. So many systems use approximations of LRU that are easier to implement, like algorithms based on reference bits or clock-based algorithms, second chance.
And what's this idea of thrashing that can happen with memory? It sounds like something my computer does when I have way too many browser tabs open.
That's a perfect analogy. Thrashing is a critical, detrimental state a system can get into. It happens when a process doesn't have enough memory frames allocated to hold its currently active pages, its working set. As a result, it constantly experiences page faults.
So it's always swapping.
Exactly. The OS is spending almost all its time swapping pages in and out between RAM and the disk rather than actually executing instructions. The CPU utilization plummets because the CPU is often idle, waiting for pages to be loaded. It feels like the system grinds to a halt, even though the disk drive might be working furiously. It's like a chef endlessly shuffling ingredients between the fridge and the counter, spending no time actually cooking. Adding more processes to the system can actually make thrashing worse in this state.
Okay, avoid thrashing. Beyond managing this active memory space, the OS also manages all our permanent files, right? It's like the ultimate digital filing cabinet, making sense of all our documents, photos, applications.
Exactly. File management is another huge responsibility. It refers to the whole set of processes and techniques the OS uses for creating, organizing, storing, retrieving, manipulating, sharing, and controlling access to files on secondary storage devices like disks.
And we interact with these systems constantly.
Constantly, whether it's using Windows Explorer, the Mac OS Finder, a Linux file manager like Nautilus or Dolphin, those are all interfaces to the OS's file management system. But the concept extends to specialized systems too, like network-attached storage, NAS devices, cloud storage services, Dropbox, Google Drive, content management systems, CMS, for websites, version control systems like Git for source code, and even database management systems, DBMS, like MySQL or PostgreSQL, which manage data within structured files.
So the file manager part of the OS is doing the work behind the scenes, allocating space, keeping track.
That's its core role, yes. When you save a file, the file manager has to find enough free space on the disk, allocate that space to the file, and update internal records like directory entries and file allocation tables to know where the file's data is stored. When you delete a file, it deallocates that space, marking it as free again. When you read a file, it uses those records to find the data on disk and read it into memory. It also handles writing any changes back to the disk.
And it organizes things hierarchically.
Usually, yes. The typical digital hierarchy builds up. Individual bytes, like characters, combine to form meaningful data fields, like a name or a price. A collection of related fields forms a record, like all the info about one customer. A collection of related records forms a file, like the whole customer list. And files are organized into directories or folders, which are themselves special types of files that list other files and directories and their attributes, like name, size, location, permissions.
That makes sense. And how does file security work? Who can read, write, or execute a specific file? How does my computer know I can open my document, but maybe not yours?
That's controlled through file permissions and access control mechanisms managed by the OS. A common conceptual model is the access control matrix. Imagine a big grid where the rows represent users or groups of users, and the columns represent files or other objects. Each cell in the grid specifies the access rights, like read, write, execute, delete, that a particular user has for a particular file.
A big permission table.
Essentially, yes. In practice, implementing a full matrix can be inefficient, so systems often use condensed methods. For example, Unix-like systems, Linux, Mac OS, associate each file with an owner, a group, and define separate permissions for the owner, members of the group, and others, everyone else. These permissions are typically read R, write W, and execute X. The OS checks these permissions whenever a user tries to access a file. It's a fundamental layer of digital privacy and system integrity.
We've now arrived at the storage itself, the hard drives or SSDs, where all our data lives more permanently. But even here, the OS still has a job to do and manage how it accesses that data efficiently, right? This gets us into disk scheduling.
Indeed. Modern computers primarily rely on disks, whether traditional spinning hard disk drives, HDDs, or faster solid-state drives, SSDs, for long-term, non-volatile storage. While magnetic tapes are still around, they're now mainly used for archiving and backup of infrequently used data because their sequential nature makes access time very slow. Disks, which allow direct access to data blocks logically mapped onto sectors, are where your active operating system, applications, and user files reside.
And the OS has to manage access to these disks efficiently, because they're often slower than RAM.
Exactly. Disk access is often a major performance bottleneck in computer systems because mechanical movement in HDDs or even flash memory operations in SSDs are orders of magnitude slower than accessing RAM or CPU registers. So it's a key responsibility of the operating system to use the disk hardware as efficiently as possible.
And what does efficiently mean when we're talking about a disk? Is it just about raw speed?
It primarily means two things: achieving fast access time and maximizing disk bandwidth. For a traditional HDD, access time is made up of two main physical components: seek time, which is the time it takes for the disk arm, carrying the read-write heads, to physically move across the platters to the correct cylinder or track where the data resides; and rotational latency, which is the additional time spent waiting for the disk platter to rotate around until the desired sector is actually under the read-write head.
So move the arm, then wait for the spin.
Right. Seek time is usually the more significant component. Disk bandwidth is then the overall rate at which data can be transferred, typically measured in bytes per second. It's the total bytes transferred divided by the total time from the first request until the last transfer is complete.
So when multiple programs all want to read or write to the disk at the same time, the OS has to manage those requests, put them in a queue.
Precisely. If a process requests I/O from the disk and the disk drive is already busy servicing another request, the new request is typically placed on a queue of pending requests for that drive. The OS's disk scheduling algorithm then decides the order in which to service these pending requests from the queue, with the goal of improving overall access time and bandwidth.
So the OS applies algorithms here too, just like with CPU scheduling, to literally decide the sequence in which the read-write head moves across the disk platter.
Absolutely. And the choice of algorithm can have a significant impact on performance. The simplest is, again, first come, first serve, FCFS.
Just handle requests in the order they arrive. Seems fair.
It's fair and easy to implement, but it's generally not the most efficient in terms of head movement. Imagine the disk head is currently at cylinder 53. If the queue of pending requests is, say, 98, 183, 37, 122, 14, 124, 65, 67, FCFS would just jump back and forth wildly, 53 to 98, then way out to 183, then back to 37, then out to 122, and so on. Lots of seeking.
Yeah, that sounds like a lot of wasted arm movement. There must be a better way to minimize that physical travel time.
There is. A common improvement is shortest seek time first, SSTF. This algorithm selects the request from the queue that requires the minimum seek time from the current head position. In other words, it services the request that is closest to where the head currently is.
Okay, so find the nearest pending request and go there next.
Exactly. Using our previous example, head at 53, Q98, 183, 37, 122, 14, 124, 65, 67. SSTF would likely go from 53 to 65, then 67, then down to 37, then 14, then jump out to 98, 122, 124, and finally 193. This significantly reduces the total head movement compared to FCFS.
That sounds much faster. But is there a downside? Does someone get left behind?
That's the potential problem with SSTF. It can cause starvation. Requests for tracks far away from the current head position might get repeatedly postponed if new requests keep arriving that are closer to the head. The distant request might wait indefinitely. It's not inherently fair.
Okay, so faster on average, but potentially unfair. What about algorithms that try to be fair and efficient? Like an elevator that keeps moving in one direction, picking up passengers on his way.
That's a perfect analogy for the scan algorithm, often called the elevator algorithm. The disk arm starts at one end of the disk and moves towards the other end, servicing all requests in its path as it goes. When it reaches the other end, it reverses direction and moves back towards the starting end, again servicing all requests along the way.
So it sweeps back and forth.
Exactly. It guarantees that every request will eventually be serviced, preventing starvation. Using our example, if the head starts at 53 and is moving towards 0, it would service 37, then 14. Then it hits the end, 0 reverses, and services 65, 67, 98, 122, 124, and finally 183 on its way out.
Okay, that sounds pretty good. Is there a variation on that?
Yes, there's C-scan, which stands for circular scan. It's designed to provide more uniform wait times. Like scan, the head moves from one end of the disk to the other, servicing requests along the way, say from 0 to the highest cylinder, 199. But when it reaches the far end, instead of reversing and servicing requests on the way back, it immediately jumps back to the beginning, cylinder 0, without servicing any requests on the return trip. Then it starts its sweep again from 0 towards 199.
Huh. Why only service in one direction?
It prevents a bias where requests near the middle get serviced more frequently than those near the ends. With C-scan, once the head passes a cylinder going outwards, requests for that cylinder have to wait for almost a full sweep before being serviced again, giving more uniform waiting times for all locations.
Are there even smarter versions that don't necessarily go all the way to the end of the disk if there are no requests out there?
Indeed there are. Those are Look and C-Look. They are optimized variations of scan and C-scan respectively. Instead of moving all the way to the physical end of the disk, cylinder 0 or the maximum cylinder, the arm only travels as far as the last request in its current direction and then immediately reverses. It looks ahead for requests.
So it avoids unnecessary travel over empty tracks.
Exactly. Look behaves like scan, but reverses direction as soon as it hits the final request in that direction. C-Look behaves like C-Scan, but only goes as far as the last request in the outward direction, then jumps back to the first request in the queue, which is the closest one to the start, without going all the way to cylinder 0, and starts servicing outwards again. These generally reduce seat times further compared to Scan-C-Scan while maintaining fairness. Look is often a good practical choice.
So what does this all mean for us, the user, sitting at our computer, just trying to open a file or save our work?
It means that a seemingly simple behind-the-scenes choice by the operating system, which disk scheduling algorithm to use, can have a very real, tangible impact on the performance you experience. It can drastically change how fast your data loads or saves, especially when the disk is busy with multiple requests. It affects how responsive your system feels.
Wow. Okay. From the tiniest electrical switch inside a transistor,
Yeah.
all the way up to these complex algorithms managing how the hard drive head moves. It's clear there's an absolutely incredible, mostly unseen dance of logic, electricity, and intricate software working tirelessly behind the scenes of every single digital action we take.
Indeed. It's quite something when you unpack it. We've explored how those simple zeros and ones become everything from a letter on your screen to a full-motion video. We saw how the CPU and memory work together in that rapid fetch-execute cycle, and how the operating system acts as the master conductor, juggling multiple programs, cleverly managing finite memory, and meticulously organizing your files and disk access to keep things running smoothly and efficiently. The layers of abstraction built upon simple foundations are truly remarkable.
Yeah. Here's where it gets really interesting, I think. The next time your computer feels maybe a bit sluggish, or maybe when you just marvel at how seamlessly you can switch between, I don't know, a dozen different applications, remember this deep dive. You now have a much clearer understanding of the hidden complexity, the incredible engineering that allows all of it to function at all. It's really like pulling back the curtain on a truly magnificent and mind-bogglingly fast stage performance.
It really is. And thinking about all this naturally leads us to wonder, doesn't it? Given these foundational principles, the bits, the logic, the scheduling, the memory tricks, what revolutionary advancements are just over the horizon in computing? Advancements that will still be built upon these fundamental concepts, but just expressed or combined in ever more ingenious and powerful ways.
That is a provocative thought. Definitely something for you to mull over until our next deep dive.